Hello everyone. So again, welcome back to our latest lecture session. So until now, I guess we were discussing precipitation and dissolution, and I believe in the last couple of sessions we have been looking at applications, right? And I think in the last session we have been looking at the addition of coagulant in the form of FeCl3, right? And how, let's say, the relevant precipitation and how the effects on sweep flock and also charge neutralization go through, right? Let's just quickly have a brief about what we discussed. So we were adding a source of Fe3 plus, right? And we saw that under when there is no alkalinity, right? That the pH fell to 3.5, right? Upon addition of this source of Fe3 plus. And why is that? Obviously because ferric hydroxide complexes are formed, thus releasing H plus, right? So thus obviously you would expect a drop in pH, and that's why I believe we saw that the pH dropped to 3.5. Yes, and I think we saw around 98% precipitation of the Fe3 plus, right? And in the second case, we looked at a case where we had some alkalinity and also initial pH of 8.2 or 8.3, I think, right? And then obviously because you have alkalinity, what is alkalinity now? It's acid neutralizing capacity, right? So again, in that particular system, we had HCO3 minus, right? And thus obviously it can neutralize any protons or H plus released into the solution. Thus I believe you saw that after addition of this FeCl3, right, you did not see a great drop in pH. I think the final pH was around 7.1 or something like that, right, after addition of FeCl3. And we saw that it was still around 100% what do we say, precipitation of Fe3 plus, yes. Right, and this is what we understood that, right, in general we know that the flocculation or coagulation goes through in two mechanisms, right, primarily anyway. So one would be charge neutralization and the other one would be the sweep flock mechanism. Obviously for the sweep flock mechanism you need to have, what do we say, the precipitate being formed, which in this case is the ferric hydroxide, right. If you remember that, we had the FeOH thrice solid being formed, right, and thus will assist in the sweep flock, right. But obviously there is no point in adding any further base, right? That was a part of the question too, because adding further base would only increase the net negative charge, right, or decrease the net positive charge on the complexes, if any, and that obviously would not assist in charge neutralization in any manner. So obviously, you know, as it is for this particular scenario of pH 7.1, where we had more or less 99% or 100% precipitation was good enough. And we did not need to add any further base. That was our particular logical reasoning the last time, right? So let's say for now we are partly done with precipitation, and obviously we are going to look at the other relevant aspect, which is solubility, right? I guess you know that's self-explanatory, right? I think the process of the solid dissolving into what do we say, aqueous species. That's what I believe we discussed in the initial class, right? So obviously, how am I going to measure solubility though? It's the amount of solid that will dissolve or that dissolves per unit volume of solution at specified conditions, I guess, right. So again, the amount of solid that would dissolve per unit volume of the solution, right, or more or less the total amount of your particular what do we say, compound that would be in the solution, right. Amount of solid that dissolves would more or less be equivalent to the total amount of your particular compound that will be in the solution, yes. So let's look at how to go about this now. So let's say by hand, how are you going to go about it, right. So here obviously you are going to start with the assumption that there is solid phase in equilibrium with your water. As in, let's just take an example. Let's say I have some precipitates here, and this is my water here. So there is going to be equilibrium between the solid phase and the aqueous phase. Right now I want to find out the concentration of the relevant compound, let's say in the water or aqueous phase, that's going to be in equilibrium with my solid. As in, if the solid was CaCO3, right, you know that it's going to be in equilibrium with Ca2 plus and CO3 2 minus, right. And so obviously what are we trying to find out? We are trying to find out the concentration of this calcium. But keep in mind that when we talk about what do we say, solubility, we are not just talking about, let's say, the free metal or such, though. We are talking about the total concentration. As in, when we talk about solubility, we are talking about Ca total per unit volume or Ca total, right? It's not just Ca2 plus. Why is that? Because as you know, there can be other complexes formed and such, but we consider them to also be soluble species. For example, in this case, we can have calcium hydroxide complexes formed too, right? But still that will add to the total calcium that's present in the aqueous phase, right? So whenever we calculate solubility, we don't calculate just, let's say, Ca2 plus or such or the free metal, we calculate the total component, I guess. Yes. So let's see how to do that by hand. Obviously, let's say, you know, in your component balance equations, you have X total, right? And let's say you have one other or specified variable, usually pH, right? So for example, the question, not question, I guess, the scenario would usually be, you have this solid present, let's say CaCO3, and let's say the pH is around 7, right? So what would be the total concentration of calcium present in the solution? So that's nothing but calculating the solubility. So again, that's just setting up the balance equations. So you can set it up X total, or let's say in this case Ca total, right, as a function of H plus, right, as a function of H plus, and then just solve for it because you know the pH, I guess, right. So again, that's relatively straightforward, but thus I'm going to skip that, but we'll look at how to get this done by Vmintech, right. So let's move on to Vmintech, right, and here I'm going to specify the possible infinite solid. So there are different aspects here, as you can see, you can specify an infinite solid phase or you can specify a finite solid phase, right. Again, the key is that, let's say, if you have relatively little or very little solid phase, right, so it obviously will dissolve, right, but we don't know if the equilibrium will be reached before the solid has completely dissolved, right, or it hasn't reached equilibrium even after all the solid has dissolved, right. So obviously, let's say, you know, we have only 1 gram per liter or a finite solid, so that you can specify in the specify finite solid phases. But let's say you are looking for an infinite solid, as in there is an inexhaustible amount of your particular solid that's going to be in equilibrium with your solution, right. So you are going to use, let's say, specify infinite solid phases, right. Again, I'm going to try to you know, explain this in a better manner, hopefully. So when you talk about specify finite solid phases, in which scenario would you look at? Let's say when you have a limited amount of solid, right. And why does that matter? Let's say I have 1 gram and it's of relevant solid, and that's in equilibrium with, let's say, 1 liter of a particular solution. Rather than 1 gram, let's choose 1 milligram, I guess, right. So let's say rather than 1 gram, I have 1 milligram of solid, let's say, and that will be in equilibrium with, let's say, 1 liter of water, let's say, right. So here, let's say, you do not know when the equilibrium will be reached. Will the equilibrium be reached, let's say, after 0.25 milligrams has dissolved, right, or 0.75, or let's say when, let's say, 1.5 milligram dissolves in the liter of the solution, right. So you don't know when the equilibrium will be reached, right, or the amount of solid that needs to dissolve before the equilibrium is reached between the solid and the aqueous phase, right. So thus, obviously, when you have limited amounts of solids present, you are going to have to specify that, right, in your particular Vmintech, and obviously if you have infinite solid, you are going to choose the relevant option there. So for one example, we are going to choose, let's say, an infinite solid phases, right, and here I am going to choose calcite, right, a source of CaCO3, and where is that? Okay, here it's calcite. I am going to say add, right, back to main menu. So again, what are we trying to set up? I am trying to set up the question in such a way that I have an infinite amount of calcite, right, or source of CaCO3, the solid, and that's going to be in equilibrium with my particular water, right. And what's the final concentration or the total concentration of calcium that's going to be present in the water. So how do I do that? Obviously, I need to specify some pH. So let's say we'll go with at neutral pH, right, and let's just run Mintech. And obviously you have, you know, calcium, just the free what do we say, compound, right, Ca2 plus, right, and also the relevant complexes CaOH, right, CaHCO3 plus, and so on. But this is not what I want. What do I need? I need the total component or Ca total, and this is what I have 3.84 into 10 power minus 3. So, for this particular condition, right, what is the solubility of this calcium here? It is 3.8 into 10 power minus 3, right. And keep in mind that it is going to be different from your just the Ca2 plus the cation, right, which is 3.7 into 10 power minus 3, but obviously considering the relevant complexes or such, the Ca total is going to be relatively higher, and this is the solubility, right, 3.84 into 10 power minus 3. So, let us just try to increase the pH and see if that is going to cause any particular change here, right. Let me go with 9, right. Okay, and equilibrium mass distribution. So, I think it decreased, right, it actually decreased, that is what you see here, and that is what you see here too with increase in pH. I guess that is what something we should have expected to, right. So, here you see that the total solubility or the solubility of calcium decreased, and it is now 3 into 10 power minus 4 here, right. And again obviously the cation is going to be at a relatively lower concentration. Why is that? You have the relevant complexes taking up the share of this particular calcium, right. So, let us go back to the main output menu, let us do it at lower pH, let us say at around 3. So, let us find out the relevant solubility here, right, and it should be obviously at relatively high concentration, and here that is what we see here, that the calcium concentration is at relatively high value. What is it now? 10 molar concentration, I guess, right. So, at pH 4 we had, what is it now, we have concentration, or pardon me, solubility of calcium at 10 molar or 11 molar, right. But at pH 7 and I think at pH 9 we saw that it was at 10 power minus 3 and 10 power minus 4 concentration ranges, right. So, let us just try to understand this for a second, I guess. So, let us try to understand why we see such a change obviously. So, the relevant reaction is CaCO3, the solid, that is going to be in equilibrium with Ca2 plus and CO3 2 minus, right. So, and I think we looked at 3 cases. One was at pH 7 when the concentration was in the order of around 10 power minus 3, and pH 9 when the concentration was in the order of around 10 power minus 4, and pH 4 I guess, and the concentration was in the order of 10 power 1 I guess, right. So, why this particular variation, or why this particular increase in solubility, right. So, more or less what do you see as you decrease the pH, right, or maybe I should have written this pH 9 here, right. So, as you decrease the pH, you see that the solubility is increasing, right. As you decrease the pH, you see that the solubility is increasing, yes. And why is that? Let us just try to understand the system. So, let us say at higher pH, let us say at pH 9, let us say, right, yes. So, CO3 2 minus concentration, as you know, will be relatively high, right. At pH 9, again, where is this from? From our acid base relevant background, right. So, this is H2CO3, right, and this is going to be HCO3 minus, and this is going to be CO3 2 minus, right. And we know that pK1 is 6.3, pK2 is 10.3. So, as we are approaching, let us say 9, let us say, right, somewhere around here, you know that CO3 2 minus is going to be present, right, and also HCO3 minus, yes. So, again at what is it now, pH 9, the CO3 2 minus concentration is relatively high, and at pH 7, right, around here, you see that there is going to be no CO3 2 minus concentration, right. At pH 7, you see that there is no CO3 2 minus concentration. So, I am going to say at pH 7 it is almost equal to 0, and same case with pH 4, it is equal to 0, right, or if not almost, slightly I guess, right. But at pH 4 you know that CO3 2 minus is not going to exist in solution. So, why is this important now? As this calcite dissolves and forms Ca2 plus and CO3 2 minus, right, yes. So, when will the equilibrium be reached now? You are going to look at the saturation values, yes. But if the CO3 2 minus concentration is high, right, Yes, what does that mean now, right? The equilibrium will be reached earlier, right? But let's say, as in, think of this now, if I increase the CO3 minus concentration, the reaction towards the left would be favorable. But if I decrease the concentration of CO3 minus, which is what I would observe at pH 7 and pH 4, right, which reaction would be favorable now? The reaction going from left to the right, or the dissolution reaction? Makes sense, hopefully, right? As I decrease the CO3 minus concentration, right, I am removing one of the products. So CaCO3, the calcite would want to dissolve, right, or the dissolution reaction would be promoted. But obviously, as I keep increasing one of the products, as in CO3 minus, or let's say Ca2 plus, but in this case, obviously, we are looking at pH and the carbonate system here, and that's why CO3 minus concentration. So as I keep increasing the product here, it would want to form the reactant here, right, or the reverse reaction would be favorable. So that is why the calcium concentrations would be obviously lesser, and that's what we see out here, I guess, right. Again, so this is with respect to solubility. So by hand too, whenever you calculate, you need to calculate X total and not the relevant cation or anion. That's something that's important. Again, why is that? You are talking about the solubility, right? The total solid that would dissolve, or let's say that's going to be in the dissolved phase, the total solid, let's say, right? And okay, so we are done with this, and we will move on to the next relevant aspect. So it's competitive precipitation as it. So until now, obviously, we have looked at cases, right, when we considered only one particular solid or one form of the solid. So with time, we know that it can form more stabler forms, right? I think amorphous to crystalline, and then remarkably insoluble crystalline phases, and so on. But more or less with respect to only one type of solid, though, right? So in general, as we know, because they are more stable or relatively more insoluble, the most insoluble forms would be formed last, right? I think we looked at this particular case as in falling down the ladder, right? The most insoluble form will be formed last. The most soluble form would be formed first. Usually most soluble forms, what are they? The amorphous forms, right? And usually insoluble forms, they are the different types of the crystalline structures, I guess, right? Crystalline forms, yes. And this is the way it would go through. And why would it try to be in the form of the most insoluble or the crystalline form? Because that's the most stablest form, right? And obviously, everything in nature tends to be at, what do we say, or reach its more stabler state, yes. So, but this, as you can remember, I guess, we looked at only one particular kinds of, what do we say, solids, as in AlOH3 solid, then the amorphous to crystalline, or so on, right? But here, let's say, you know, different, what do we say, metals can precipitate out in different forms now, right? So, for example, you know, you can have CaCO3 precipitate out, and you can also have calcium precipitate out in the form of CaOH twice, right? So the key here is obviously it's competitive precipitation, right? But in general, obviously, in the solution, only one particular solid will predominate or will precipitate out. So you want to be able to figure out which particular solid will, you know, predominate or precipitate out under the given conditions, right? And again, why is that important? Because depending on the type of solid that precipitates out, the relevant concentration of Ca2 plus will be dependent upon that, what do we say now, solid, right? Again, this is more or less similar to the controlling solid, right? So here, though, we have different types of solids. So how do we go about it? So the key here is that, you know, anytime the system will try to be relatively more stable, system tries to be stable, right? And what does that mean? That means it prefers the insoluble solid. So the preference is always for the most insoluble solid. As in, what does that mean? It means that the energy of the system, I guess this is the way to understand it, right? The energy of the system is relatively less, or Gibbs energy, right? G system, this is something we discussed in some of the earlier classes too, is going to be relatively less, right? Or the system is going to be more stable when you have the more insoluble form. So what does this having this more insoluble solid form mean, I guess? So whichever, let's say, you know that CaCO3 solid can be in equilibrium with Ca2 plus and CO3 minus, and you know that CaOH twice, the solid will be in equilibrium with Ca2 plus and OH minus, right? So, but obviously in solution you won't have two different concentrations of calcium, right? You will only have one particular concentration of calcium. So you want to know which one, which solid would precipitate out, right? So obviously we are saying that the more insoluble form will precipitate out. What does it mean? So more insoluble form means that particular solid which will give the minimum concentration or the lesser concentration of, let's say in this case, calcium will predominate, right. So what is it that we are trying to say? As in, if the calcium Ca2 plus that is in equilibrium with CaCO3 solid, let us say, if that is going to be less than the calcium that is going to be in equilibrium with the CaOH twice solid, right. So what does this mean now, right? That CaCO3 in this particular scenario is more insoluble, that is why CaCO3 will precipitate out. But obviously let us say if the Ca2 plus that is going to be in equilibrium with CaOH twice solid is lesser in concentration to the Ca2 plus that will be in equilibrium with CaCO3 solid, right. What does that mean? CaOH twice will precipitate out in this particular condition, right. So whichever particular solid is more insoluble, meaning whichever particular solid will lead to the metal concentration or the relevant anion being at, or in general cation, let us say, right, being at lower concentration, that is what the system will favor, and that is what we are trying to see, right. So let us try to take this further, I guess. Let us try to see, set up one particular equation for this. So one case I am going to look at now, which we are going to use later is, so obviously there will be one particular scenario when the concentration of calcium in equilibrium with what is it now, CaCO3 will also be equal to the concentration of calcium in equilibrium with CaOH twice solid, right. So let us try to plug that in, I guess. So what am I trying to do here? I am trying to plug in Ca2 plus CaCO3 solid, right, is going to be in equilibrium with the Ca2 plus in equilibrium with CaOH twice solid, right. So the Ca2 plus concentration that at a particular scenario, right, the calcium that would be in equilibrium with CaCO3 is going to be equal to the calcium concentration that would be in equilibrium with CaOH twice, right. At that point you will have both the solids precipitating out, right. So when those two concentrations are same, what does that mean? Obviously both the solids will precipitate out. So let us just try to write down the relevant or equation, I guess, right. So here what is the equation here? We know that K solubility product for CaCO3 is going to be equal to concentration of Ca2 plus into concentration of CO3 2 minus, right. And here K solubility product of CaOH twice is going to be equal to concentration of Ca2 plus times OH minus square, right. So obviously here the concentration of calcium Ca2 plus in equilibrium with CaCO3, right. What is that going to be equal to? K CaCO3 by CO3 2 minus. I mean, you do not need to mug these up, but let us just try to understand where we are going to end up, I guess, right. So this is one relationship for the Ca2 plus CaCO3, right, and the other one here, and how can I express this? Ca2 plus at CaOH twice, right, is going to be equal to KCaOH twice by OH minus square, right. And again, what are these equilibrium coefficients? Nothing but the solubility constants or the solubility products, right. So here let us say, but in the second case, to have it expressed in terms of H plus, if I multiply it by what now, or OH minus, if I express that as Kw by H plus and then transform it, and Kw, let us say I consider that to a constant. So let us say I will call this this thing K star, let us say CaOH twice K star into H plus square, and obviously what is this K star CaOH twice? That is nothing but KCaOH twice by Kw square in this particular case, right. I am just trying to express OH minus as Kw by H plus and the relevant transformation. So here I have the other relationship, and now I am going to equate these two as I see fit here, right. So what do I have? Solubility constant CaCO3 by concentration of CO3 2 minus, right, is going to be equal to K star CaOH twice into H plus square, right. So again, what is it that we are trying to develop, right? We are trying to develop or understand the system when both these solids can precipitate out. That is why we have the concentration of calcium that would be in equilibrium with each of the solids to be equal, only then will we have both the solids precipitating out. So right, you don't need to obviously mug up these derivations or such, but obviously you need to understand how to get at them or understand the basics. So again, let's get this further. So we are going to have K CaCO3 is equal to K star CaOH twice into H plus square. And what is CO3 2 minus, right? It's nothing but alpha 2 into CO3 total, right? So for a total alpha 2, right, I think let me just write that down for the sake of, so what is alpha 2 now? Alpha 2 is nothing but CO3 2 minus by H2CO3 plus HCO3 minus plus CO3 2 minus, which is nothing but CO3 total. So the concentration of CO3 2 minus is alpha 2 times the second or the third ionization fraction times the CO3 total, and that's what we have here. So when this particular relationship is met, right, you will have both the solids precipitating out, right. So before we go further, let's just try to understand when, or visualize, I guess, when is it that your calcium hydroxide is going to precipitate out, and when is it that the calcium carbonate is going to precipitate out. So obviously for this, let's look at an log CpH graph that I have in the next slide. So obviously the key here is that to understand which solid will precipitate out, you need to see that the calcium concentration that's in equilibrium with that particular solid will be lower, right. Why is that? Because the system wants to be at a relatively more stable state. So here what do we have here? So we have log C here, and obviously it should be pH here on the x axis, right. So log C, I guess. So what do you see here? Let's just try to understand the system here. Let's just look at the solid line for here now. So this is the Ca2 plus that would be in equilibrium with calcium carbonate, and this is the calcium concentration that will be in equilibrium with calcium hydroxide, right. So what do you see here? You see that Ca2 plus CaCO3, this is the trend for this particular case, right. For CaOH twice the calcium, this is the trend, right. So obviously in all this region here, right, until here, let's say, until this point, which particular what do we say solid will predominate? Obviously that particular solid which will give the lowest concentration of calcium. So obviously as you see that in this region, the Ca2 plus at CaCO3 is less than the Ca2 plus at CaOH twice. So obviously until this pH, right, that where you see this intersection here, this is from theoretical log C pH graph, right, you can get this from Mintek or such. So again you see that CaCO3 will thus predominate in this particular region. Again, why is that? Because in this region, as you can see, Ca2 plus in equilibrium with CaCO3 is going to be less compared to the Ca2 plus that's going to be in equilibrium with CaOH twice, right. But obviously as you see in this particular region here, or in this particular region here, right, and now where is the CaCO3 concentration here? It's out here, Ca2 plus in equilibrium with CaCO3, right, the red line, but the green line is the Ca2 plus that's in concentration with your, what is this now, CaOH twice. So as you see in this particular region, the Ca2 plus in equilibrium with CaOH twice is less than the Ca2 plus that's in equilibrium with CaCO3, and thus obviously in this particular region CaOH twice is going to predominate, right. So again now this is good. So again let's try to understand this. So at remarkably high pH, CaOH twice, the solid is going to be precipitating out. So again, why is that? If you want to look at it, it's nothing but CaOH twice, right, is going to be in equilibrium with Ca2 plus and 2OH minus, right. Yes. So at remarkably high pH, what's happening here? So at very high pH, OH minus concentration is going to be very high, right. So as in then which particular what do we say, the forward or the backward would be favorable? You would see that the backward reaction would be favorable, right. So that would obviously lead to what now? More precipitation of CaOH twice and leading to lesser concentrations of Ca2 plus, right. So that's why you see that with increasing pH, the calcium concentration that would be in equilibrium with CaOH twice keeps decreasing, right. Again, why is that? Because as you keep increasing the pH, the OH minus concentration keeps increasing, and now the backward reaction would be relatively more favorable, right, and thus you would have more precipitation in the form of CaOH twice, leading to further decrease in the calcium concentration that would be in equilibrium with the CaOH twice, the solid. And that's why you see that at remarkably high pH, the CaOH twice predominates or will precipitate out, pardon me, and at it's not lower pH, relatively lower pH, CaCO3 would control, right. So that's the particular aspect here. So and one other aspect that I want to point out here is, right, so let's look at now, let's say if you increase the concentration of CO3 total. So this particular solid line was at one particular CO3 total, right, and here let's say here we have CO3 total 1 and here we have CO3 total 2, right, which is greater than CO3 total 1, and that's what we say here. So before we go further, let's just try to understand what this means for the system now, right. You know that CaCO3, the solid, can be in equilibrium with Ca2 plus and CO3 2 minus, right, CO3 2 minus, right. So for a given particular case of CO3 total 1, we looked at the earlier case for this solid line, right. So let's say though, but I end up increasing the CO3 total, how is the system going to change? So here if I increase the CO3 total, what does that mean? I am increasing this particular variable here. So leading to which reaction being more favorable now? The backward reaction compared to the previous case, right. So I am increasing the CO3 total, that in effect means I am also increasing the CO3 2 minus concentration, yes. So if I increase the CO3 2 minus concentration, what is going to happen now? The backward reaction is going to be more favorable compared to the previous particular equilibrium, right. And so you are going to have more of the solid precipitating out. What does that lead to? That will lead to a decrease in Ca2 plus concentration. So that is why you would see that at greater total CO3, the Ca2 plus in equilibrium with CaCO3 is going to be lesser, right, and obviously that is the explanation we looked at here, yes. So and that is why obviously the equilibrium would slightly shift out here though, right. Yes, at a particular CO3 total, this is the case where CaCO3 predominates, but when you increase the CO3 total, you see that there is a much higher range to which at which CaCO3 would precipitate out. Again, this is for our particular understanding, right. So let's move on to the other particular aspect. So here I guess we have predominance area diagrams, yes, and so I believe we are running out of time. So I will just briefly look at what it is that we need to understand or try to understand from these predominance area diagrams, and we are going to continue this in the next session. So the name is self-explanatory, right, it is predominance area diagrams. So for example, let us say you are trying to understand a system and you do not have, let us say the time or the patience to go through that in relevant detail or look at VMINTech, let us say. So these obviously predominance area diagrams will give you a snapshot, right, overview of those particular regions, right, at which a particular compound is going to predominate. So that is obviously nothing but the predominance area diagrams, right. So I guess with that I will end today's session, and we will continue discussing this precipitation and dissolution relevant aspects, and hopefully get it done by the next session, I guess, and thank you.